Welcome back to the next video, everybody. 20 videos later, we are finally ready to use what we've learned over the past 19 videos in the playlist to finally state the precise version of the modularity theorem and use its semi-stable case to give a proof of Fermat's last theorem. As of this video, chapter 1 of my notes is available on my website. Link is in the description. Let's get into it. So here's the modularity theorem. Here's what it says on a basic level. Let E over Q be an elliptic curve. Then E is modular. Over the past several videos, I've given you a lot of different ways of thinking about the modularity of an elliptic curve. If you haven't seen those videos, I would recommend checking them out first. Playlist link in the description. Here's the precise statement of modularity. There is a bijection between Q isogeny classes of elliptic curves E over Q with conductor N and normalized new forms F in S2 of gamma 0n with rational coefficients. And this correspondence matches up the L function of the elliptic curve with the L function of the new form. Okay, so let's prove precise modularity, assuming basic modularity. One direction was taken care of entirely in the last video, so please watch that. That's the direction where I give you the new form and we spit out the elliptic curve. Conversely, let's start with an elliptic curves and let's assume basic modularity and prove the other direction of precise modularity. We already know from a previous video that Q isogenous elliptic curves have the same primes of each reduction type, and so they have the same conductors. Well, weight two new forms of conductor N and number field Q are definitely determined by their Fourier coefficients. And the Fourier coefficients of L functions of Q isogenous elliptic curves over Q match, as we proved in a previous video. And so if you take those two things together in tandem, you see that the new form produced by the basic modularity theorem is definitely Q isogeny invariant. The fact that the new form is unique and the fact that its coefficients are rational are clear by the matching of the L functions. Okay. And the fact that the conductors on each side of the bijection match follows from the fivefold theorem, which I have an entire video on. It's one of my videos on modularity. Okay, so this isn't why you're here, right? You're here to see how to prove Fermat's last theorem. So let's do that. We're finally in a position where we're able to do that. Now, one caveat, and it's a huge caveat, we're going to only prove Fermat's last theorem assuming the modularity theorem holds, okay? So here we go. We're going to go by contradiction. Remember, we only have to prove Fermat's last theorem for exponent prime and at least 5. That's what we've reduced the problem down to. So suppose that for some prime p bigger than or equal to 5, there is a non-trivial solution ABC over the integers to the Fermat equation a to the p plus b to the p plus c to the p equals 0. Recall, as we've discussed in previous videos, we can assume a, b, and c are pairwise coprime and that a is -1 mod 4 and that b is even. Okay, because of this, we can attach to this solution E sub f, the associated Frey curve, given by y squared equals x times x minus a to the p times x plus b to the p. Okay, from proposition 1 in a previous video, we know that EF is a semi-stable elliptic curve with conductor, which we'll call n sub E sub f, given by the product over all primes L dividing ABC of the primes L. By the semi-stable modularity theorem, EF is a modular elliptic curve. And one way of interpreting that is there's a new form F in S2 of gamma 0 of n sub E sub f with number field Q, such that rho sub E sub f comma P, the p-adic Galois representation attached to E sub f, is isomorphic to rho FP, the p-adic Galois representation attached to F. So that means rho bar E sub f comma P is isomorphic to rho bar F comma P. Just residual representations have to be isomorphic as well. By theorem 2 from a previous video, rho bar EFP is absolutely irreducible, unramified outside 2p, and flat at p. And so the same must be true of rho bar FP because of this isomorphism. This means all of the conditions of Ribot's theorem are satisfied if you go back and look at my Ribot's theorem video. And what this ends up showing us is that there's actually a new form G in S2 gamma 0 of 2, so of level 2, such that rho bar GP is isomorphic to rho bar FP, which is isomorphic to rho bar EFP. But by the dimension genus formulas, look, we know the dimensions of all these vector spaces here. They're found in Diamond and Sherman, for example. Guess what? there aren't any new forms in S2 gamma 0, 2. This is a trivial complex vector space. So this new form G doesn't actually exist. That's what I'm saying. So there you go. There's your contradiction. Fermat's theorem is true, assuming semi-stable modularity. Again, I didn't acknowledge in any previous videos the dimension genus formula step, but Diamond and Sherman proves this in chapter 3. This is a well-known kind of standard easy result in modular forms. You can calculate the dimensions of all these vector spaces of cusp forms, and in fact, even of modular forms. Well, it's not that easy, but it's standard. Okay. Now, let me explain this Ribot's theorem step more carefully. It's the last thing I want to do. Once we reach the Ribot's theorem stage of the proof, we have a weight 2 new form of conductor N given by the product of all primes L dividing ABC. This conductor is certainly even because remember B is even, and it's definitely not just 2 because remember A is -1 mod 4. That means I can write N equals 2 times L for some L, which is a product of distinct odd primes. The reason for that is the Frey curve is semi-stable. So its conductor is square free. It's a product of distinct primes. So L is definitely odd, and it's also a product of distinct primes. So this is all by semi-stability. Okay. Now, let's take a prime little L dividing big L. If little L is P, then I know rho bar FP is flat at P by theorem 2. If L isn't P, then since L is odd, rho bar FP is unramified at L, also by theorem 2. Theorem 2 is from a previous video. Okay. If you go back and look at my Ribot's theorem video, you see then that all of the conditions to use Ribot's theorem are satisfied, essentially thanks to theorem 2. And so what we do is we apply Ribot's theorem iteratively, prime by prime, canceling away all the odd primes L, which are all distinct, until we're left with, well, what happens if you use Ribot's theorem to cancel one prime away at a time from big L? You end up canceling big L because L is odd, and you're left with a new form G of conductor 2. So actually what's going on here is you're using Ribot's theorem several times, okay, potentially. All right, there's the proof of Fermat's theorem. So starting next video, we're going to go on to chapter 2 of my notes. And there we will begin looking at an overview of the proof of semi-stable modularity. So I'll see you then, and thanks for watching.